Hello, this is a tutorial on Introduction to Binary Numbers and Character Encoding. So in this tutorial, we will learn about binary numbers. We will have a brief introduction to why they are required and what led to their use in computers. After that, after briefly studying about binary number basics, we will move on to converting binary numbers to decimal numbers and vice versa. And following that, we will be representing characters with numbers, and we will be discussing how characters are stored in memory. And finally, we will end our tutorial by seeing some basic operations on binary numbers. So let's start this tutorial. So first of all, binary is a number system whose base is 2. Here you are reading that the base of binary number system is 2. So the base of decimal number system is 10, we know that. So since the base of decimal is 10, it has total 10 digits. Likewise, since the base of binary is 2, it has only 2 digits, namely 0 and 1. Now we will move on to the fact that why binary number system is so much useful in case of computers and computing devices, right? The first point is they represent an on state 1 and off state 0, which is why they are easy to represent in electronics. So from the very basic, computers are made up of electronic equipments. We all know that, like transistors, integrated circuits, others are there, that is not important, but the very basic thing is they are made up of electronic equipments. And these equipments basically works on the concept of switching. So it can be either on or it can be either off. So this kind of behavior, it is very easy to represent where the number system has only two states, specifically 1 and 0. The 1 represent on and 0 represent off. So we can use the binary number system to represent these electronic characteristics of the circuits that actually constitutes the computer in a very nice way. The second thing is laser circuitry is required to design devices if we use binary system. And also the very basic nature of computer is that they work on logical operation. A logical operation can be either yes or no, that can be either true or it can be either false. So again you see this binary kind of nature, either it is 1 or it is 0, means or it is 0, that is yes or no. This kind of thing is again popping up that we can see. So that's why we can see that binary is a good choice for computing systems. Now the second thing is the smallest unit of binary data is a bit. That is, suppose you write 1, we know that 1 is a binary digit or 0 is a binary digit. So it is 1 bit. Like in decimal numbers we say digit, right? So 1 digit, 2 digit numbers, so 1 0 to 9 are single digits. Likewise 1 and 0 are 1 bit information of binary. Bit and digit are kind of analogous, you can say. Now a string of 8 bits make 1 byte of data. So if you put a string of 8 bits, a string of 1 and 0, maybe any combination you can use. Okay, so this is 8 bits. So this is 1 byte of data in binary. Okay, now how many values can a given number of bits represent? So before moving into that, let us have an idea of how binary counting happens. So if binary is a number system, we must be able to count digits using that, right? Like in normal number system, we counted 0 to 9. So here also we can count. So how we do that? So the basic is, suppose you have 0 0, two digits are given to you and you have to make combinations on the basis of that. So 0 0 is one possible combination, 0 1 is another, 1 0 1 1. So using only two digits, that is 0 and 1, and given that you can only use two of them, there is only these four possible combinations. You cannot make any further, right? Using only 0 and 1, that is the binary digits. Again, if you do a single digit, you have been given only one digit to use, or one bit exactly to use, then either you can have 0 or you can have 1. You cannot write anything else. So given one bit, there are two possible combinations. Given 2 bits, you have 4 possible combinations. Accordingly, if you have been given n bits, right, likewise, then you can have, we are generalizing it, equal to 2 to the power n possible combinations. That's what this point says. N bits can represent 2 to the power n possible values. See, if we put here n equal to 2, then you get 2 to the power 2 equal to 4 possible combinations. So that's here you see the same thing is happening over here. So let's just for a simple example, if I have been given 3 bits, so you can have total of 2 to the power 3 equal to 8 possible combinations. Okay, so if you have 8 combinations given 3 bits, so those 8 combinations are basically representation of numbers which are in binary, but they represent the counting, right? So let's so just see how it happens. So we have been given 3 bits, so I am starting from 3 zeros. That's the most simple combination that is possible. After that we will add 1 in each step, like normal in decimal number system, the way we proceed here also we will do the same. If we add 1, it will become 0 0 1, then 0 1 0. Likewise we will have the all possible combination. So these are the 8 combinations. Now let us associate the decimal numbers with each of these with each of these numbers in the sequence. So since it is the starting number, we can associate 0, decimal 0. We can associate, after that we are just sequentially associating each of the numbers, right? So 0 to 7 we did represent, and these are the corresponding binary equivalents of these decimal numbers, right? So given n bits, let us make one quick observation. We can have 2 to the power of n combinations, right? But since we are counting from zeros, with this 2 to the power n combination, how many means up to what number are we actually representing? 2 to the power of n minus 1. Now why is it so? You see, 2 to the power n with 3 bits, n equal to 3 is 8 combinations, but we did represent up to binary decimal 7 with 3 bits, right? So 2 to the power n is 8, n for n equal to 3, and 8 minus 1 is 7, right? So that's why given n bits you can represent up to 2 to the power of n minus 1, and you can represent total 2 to the power of n combinations. Okay, so this is the rule of how to convert decimal numbers into their binary equivalent. So for the sake of reading, just have a quick look to these rules, but we will be discussing this with the help of examples just next to this. Yeah. So okay, so the first step is divide the decimal number that has been given to you by 2. Note down the remainder and divide the quotient obtained by 2 again. Okay, so here it says repeat step 1 till the quotient becomes 0. So you have been given a decimal number, you divide it by 2 and you note down the remainder. You repeat this process more than means repeat the process until the quotient that you are getting becomes 0, right? And when you get the step when which the quotient becomes 0, you will just write the remainders obtained till now in a bottom to top manner. So this is very important. If you write it in the opposite order, it will be wrong answer. You have to write all the remainders from bottom to top of the division process. So let's have a look of how to do that. Okay, so suppose we take the example of a number 1729. So first step was that we will divide this number by 2. So what will be the quotient when we divide it by 2 is 864, and you get 1 as remainder. I am writing the remainder over here. Now again you divide this quotient obtained as per the step 2, which says that repeat the step 1 until the quotient becomes 0. So whenever this value in the step becomes 0, then we will do the next step. Up till that we will just divide it. Now this is the last step, you see. So 2 zeros are 0 and we have 1 as the remainder. So here we got the quotient as 0, right? We got the quotient 0 in this chain of division. So when we get this quotient as 0 in the last step, then we will just write the remainders that we obtained till now in this fashion, right? So what will be the answer? The answer will be 1, after that another 1, okay. So this is the binary equivalent of the number 1729. This is in binary, so many times we write it as base 2 like this, okay. Subscript of that number is 2 and it is equal to 1729 in base 10. Okay, so now we are moving on into the second example, which is 2.718. Now we know that how to we read how to convert a given whole number into its binary equivalent, but we don't know how to do it for the fractional part. So let's go to the previous slide and just read how to do that, and then we will come back to the example. So here you see it's the fractional part, how to convert the numbers, right? So multiply the decimal fractional number by 2 and note down the integer part of the result. So we have to multiply the only the fractional part. So this is very important. Don't multiply the whole number. Only the fractional part we will take. We will multiply that by 2 and we will note down the results integer part. Whatever result we get, we will note down the integer part. And we will separate out that integer part, and the results fractional part we will take, and with that fractional part we will multiply 2 again. Now this process will go on, and we will every time we will separate the integral part and multiply 2 with the remaining fractional part. Now this process continues until the fractional part that we obtain becomes 0. In one of the steps, the fractional part may get to 0 and then we stop the conversion. But if we do not get 0 at any stage, suppose up to 5, 6, 7, maybe 8 stages we did and we still did not get 0, then we have to stop anyway. We have to take the call, take the decision that we have reached the desired level of precision. So we have to take the call, should we want, do we want to continue or do we want to stop up to this level of precision that we have obtained. So let's take an example. We will get back to the previous example and see how this happens. So the integral part is easy, right? We did that previously. What we will do is we will simply take 2, we will divide it by 2 and we will see that 1 is the answer, quotient and 0 remainder. We again divide it by 2, we get 0 as the quotient and obviously 1 is the remainder, and we will move like in this order since we have obtained 0 quotient. So the equivalent of 2 in decimal is equal to 10 in binary. So that is done. Now we will deal with the fractional part of 718. So let's see what was the rule. The rule was you take only the fractional part, which is 0.718 over here, and you multiply 2 with it. Let us see what is the result. The result is, you can do it using your calculator in the exam. Now what we will do, we will simply note down the the integral part separate, which is 1 over here. You see here 1, it's there. We will take the fractional part separately and we will multiply again 2 with it. So whatever result we get, that is equal to 0.872. Now here you see the fractional part is 872 and the integral part is 0. So we separated that out and we get 0.872 into 2 again, and we get 1.744. Continue the process like this. Okay, so you see that we have done maybe 6 steps we have done, and we still did not get the fractional part over here, right? Any of the fractional part we did not get 0. So we were continuing our rule. We are proceeding by multiplying by 2, right? So you see that previous, let's go to the previous slide. We checked that repeat step 2 until the fractional part is 0 or a desired level of precision is obtained. So what is the answer after we stop, after we decide to stop? So the answer will be for the fractional part, that is for 0.718 from which we started, right? We started over here with the number. It will be from top to bottom. Simply put a 0 point like the decimal part and simply write 1011 So this is the binary equivalent of 0.718. Obviously it has some errors in it because we lost a little bit of precision over here, since if we would have continued the process maybe 3-4 steps, we would obviously get better precision, but it is okay, you can take that call, right? If you get 0, then obviously it's totally correct, you are getting 100% precision, it's totally getting converted. So the whole whole conversion corresponding to 2.718 will be the decimal part and then the integral part and then the fractional part. So what will be the number? The number will be I will write it here. Okay, 10, which is for the decimal part. After that we put the point and then 101101. So this is the whole binary equivalent for the number 2.718. Now a little trivia about the numbers that we took as example. So 2.718, it's a well-known famous constant, maybe the most famous constant if I say so, which is called Euler's number and represented with E. Okay, so let's move into the second number, the initial number that we took, that is 1729. So this number also has an associated story with it. So this number was actually encountered, I would say, by a great mathematician called Hardy, and he went to visit one of the finest mathematicians that India has ever produced. It's Srinivasa Ramanujan. So he was ill and he was being treated in a hospital. So then Hardy visited him and he told him this number. There is a great story behind this. So this number is called taxicab number. You can search it over the web and you can see the story. So how to convert a binary number to decimal? The rule says that write down the bits for the integral part. Again, we will see the fractional part later. But write down the bits of binary numbers with their corresponding powers of 2. Multiply the bits with their corresponding powers of 2 and add them. So let's take simply what do we mean by powers of 2 over here? Since binary is a base 2 number, so every digit must have a corresponding base to the power value, right? So let us say you have in decimal 24 as a number. So how we get 24? Actually we get 24 as 2 into 10 to the power 1 plus 4 into 10 to the power 0. This is how we get actually 24, right? 20 plus 10 to the power 0 is 1, so we get 24. Like, so this value, that is the powers of base, in case of binary it will be simply 2 to the power of n form, right? Because the base of binary number is 2. Likewise, we will while converting from decimal binary number to decimal, we will have to represent the number in its powers of 2. So let's take an example like the previous one. So here is a binary number given and we will convert it into its corresponding decimal form. So at first let's write the number a little bit gap, with a little bit of gap in between. Now we will simply put the power starting from 0, right? So here it is 0, power is 1, power is 2, and likewise. Now we will simply write it as, since the first is 1, we will write 1 into 2 to the power of 10 plus 1 into 2 to the power 9 plus 0 into 2 to the power 8 into 2 to the power of 0. Now just put the value 2 to the power 10. You can do it on your calculator and this value will come to 1024. So 1024 into 1 will be 1024. plus 2 to the power 9 is 512 into 1 is 512 plus 0 into anything will be 0 plus 2 to the power 7 is 128, 2 to the power 6 is 64 into 1. Now you see there were 5 zeros over here, so all the terms will be 0. We will have 5 zeros over here. And finally 1 into 2 to the power of 0, 2 to the power anything you got to the power of 0 is always 1, so it will be 1. Now you do the summation and you get the result as 1729 base 10, right? So we just did the reverse calculation. If you see that this is the number that we initially got while converting from decimal to binary. Okay, so again a fractional part is coming in this example, the new example. So we go back to the rule how to do that. Okay, so the steps for converting binary number to decimal for the fractional part. Same as conversion of integer part, just the power will be starting from -1. So the power we assigned previously, so that started from 0. Now in the decimal part, in the fractional part, it will start from -1 and the process is similar. So let's see what we do. So for the integral part is easy, like the previous rule only we will proceed. So 1 into 2 to the power 1 plus 0 into 2 to the power 0. We get it as 2, right? Now we will move into the fractional part. So just write the fractional part again separately, and remember here it's the decimal point. So you put here -1, -2, -3, -4, okay, so we got this. Now again the same process continues. 1 into 2 to the power -1 plus 0 into 2 to the power of -2. Okay, done. And after this what we will do is you will simply put the values and you will add the terms. So this overall value 2 to the power -1 is 0.5. 2 to the power of -2 into 0 will be 0. 2 to the power -3 will be 0.125. Okay, so this value will come something around 0.7148, right? So this is the value of 0.7148 in decimal converted. Now again you see the total number. What will be the total number? The integral part which was 2 over here, and the fractional part which is 714.